So when I talk about cyclic alkanes or cyclic alkanes, I'm talking about these carbon, hydrogen, single bond structures, but that are now in a ring shape, okay? And so we have hinted at these, but we haven't specifically talked about them. Okay, so first we're going to talk about just kind of the general energetics of these cyclic structures, and then we're going to move into figuring out, for specifically cyclohexane, what is the best conformation that it can be in as well, okay? So now, if we're thinking about tetrahedral carbon, right, so tetrahedral carbon is sp3 hybridized. What type of bond angles do we look at with respect to tetrahedral carbon? What is the idealized bond angle here?
No,
it's tetrahedral, right? So what is this bond angle, tetrahedral?
Oh, it's like 108.
109.5, right? So perfect idealized tetrahedron has an ideal bond angle of 109.5, okay? Now, as we start to think about these cyclic structures, especially with the way that we draw them right now, we're going to see that the less carbons there are, the more condensed this bond angle is, right? So for example, if we had a 3-member carbon ring, that would form, in theory, a triangle, right? What would these bond angles all be? About 60 degrees, right? Ideally, they want 109.5. So how energetically stable do you think this is going to be if they are forced to condense themselves to 60 degrees? Not very stable, right? So really early studies of all of these cyclic structures found that the most common cyclic alkanes were 5-membered rings and 6-membered rings. So this is a 5-membered and this is a 6-membered. We have cyclopentane and cyclohexane correspondingly, okay? And again, if we're drawing these in this perfect idealized bond situation, where these are all 2-dimensional, the bond angle for cyclopentane would be 108. The bond angle for cyclohexane would be 120. Who do you think would be more stable and found more often if we wanted to try to achieve that 109.5 bond angle?
The 108.
The 108, right? So original studies of this said, okay, well, nothing below this really forms, nothing above this really forms. These are the 2 main ones. And cyclopentane, because it's going to be idealized as close to that 109.5 bond angle, is going to be more energetically stable. Now, what's the problem with the way that this person was drawing these at the time? They're 2-dimensional, right? So that's the big problem with all of these. So, you know, we're thinking, oh, look at this, perfect 108, but in reality, this is not a 2-dimensional structure like we have drawn it here. It's a 3-dimensional structure. And we're going to find that as we move up, more things are going to form because, again, they can take on a 3-dimensional shape, okay? So, problem with the original studies was that they were drawing them in 2 dimensions. Instead, these are 3-dimensional structures. And so now we can kind of look at the ability of these various cyclic alkanes and determine who really is the most stable, okay? Okay, so there's a couple things to note here. For cyclopropane, we're looking at, with respect to stability, we're looking and going back to these combustion reactions. So for all of these, the way they're determining these heats of combustion is they're taking their cyclic alkane, right? So they're taking our cyclic alkane and they're reacting it with oxygen, forming CO2 and water, right? And they're measuring the overall heat of combustion for this reaction. This is the exact same thing that we did with our alkanes to determine, oh, well, the more branched an alkane is, the more stable it is. So it's the exact same concept here, okay? Now, also note that they're normalizing this per CH2 group because what happens as we increase the number of carbons here? We're not going to get the exact same products overall, right? So to kind of normalize for that, we're going to divide whatever this heat of reaction is by how many carbon groups are actually in there, okay? So that's going to give us this overall estimate of how stable each molecule is. So we look at these, there's not a lot of difference here, but who has the largest heat of combustion per CH2 group? Cyclopropane, right? So cyclopropane, because this is the largest heat of combustion, is the least stable of all of our little cyclic alkanes, okay? So as we go from cyclopropane to cyclobutane, we see a decrease, but it's still fairly high until we get to cyclopentane. And this is when we get into the 650 range. And we kind of stay in that range as we increase the number of carbons, okay? So these guys, we'll talk about why they're so high comparatively, but after we reach 5 carbons and we continue on, we're going to see a nice stabilizing trend. Still, in this, we can get a little bit more information out of this. So we have cyclopentane here at 658. We've got cyclohexane at 653. Who's the most stable between the two? Cyclohexane. Okay, so again, this goes against what von Baer actually originally postulated with respect to this. It's actually cyclohexane, which is the most stable of all of our ring structures. So this guy is more stable than anyone, and we're going to go through the reasons why that is in the next couple of slides, okay? Okay, so least stable is cyclopropane, most stable is cyclohexane, but again, once we reach that 5 carbon cutoff, we tend to reach this nice little plateau of stability, okay? Now, first one that we're going to talk about is the least stable of all of these guys, which is cyclopropane. We're going to talk about why we see such instability. Okay, so cyclopropane, when we talk about this instability, contains a significant amount of what is called ring strain. So there are 2 different components to this ring strain, okay? There's going to be an angle strain component as well as a torsional strain. So for example, let's say I take my little model kit here, and I take 3 carbons, so I've got 1, 2, 3, and I try to make another bond. See how difficult this is? I kind of have to bend my ring-like structure, okay, to get this nice little cyclic ring. This is what we mean by angle strain. There are 2 components to this, right? Number 1, these bonds, what's in these bonds? What in bonds specifically? Electrons, right? As we bring these electrons closer together and we get this 60-degree bond angle, we're going to get a lot of steric hindrance because of that, because this electron cloud is bumping up against this electron cloud. Number 2, this sigma bond, right? When we form sigma bonds, we need that orbital overlap. How well is this overlapping as it's doing this? We'd love to get this nice, beautiful head on, but because this guy is so bent, we don't get this really efficient orbital overlap, okay? So that's 2 different reasons or 2 different things that contribute to angle strain. Now, there's another component to this, and that's torsional strain. So what is torsional strain related to? We talked about last time we had these different conformations. We had eclipsed and we had staggered, right? And the eclipsed was, right. So the eclipsed was so bad because all of those groups had that torsional strain. All of those groups were eclipsing, right? And we had talked about the reasons for that. If we go around our cyclopropane structure here and we look at the Newman projection, the problem with cyclopropane is everyone is in the eclipsed position, right? So because of this is extremely unstable, because all of this torsional strain, because of everyone in the eclipsed position. So that's also what contributes to the ring strain of this. It's not just the angle strain, it's also the fact that all of these carbons are eclipsed. Okay, so 2 different things that we're always looking at with ring strain. Angle strain, which again goes back to that non-ideal bond angle, and then the torsional strain due to all of the eclipsing interactions from the various carbons in the ring. Okay, now if we break this guy up, and we add in, I've already bent my poor little bonds, they're never going to go back to normal, and we add in another carbon, right? So that was cyclopropane, the most unstable. With cyclobutane, which is going to be our 4 carbon group, we're going to try to again make this bond. It's going to be a little bit easier, right? So that's good. So we don't have as much angle strain for cyclobutane, but we still get significant amounts of torsional strain. Okay, so for cyclobutane, again, ideally we want this to be a 109.5 bond angle. Compared to cyclopropane, it has moved from 60 to now 80 degrees. So these guys are almost 90 degrees. There's still angle strain there, but most importantly, there's still significant torsional strain. So if we look at all of the carbons down their Newman projection, these are all still in their eclipsed interactions, okay? So again, cyclobutane has significant ring strain again. So ring strain that's coming from the angle strain, which is a little bit less than cyclopropane, but there is still significant amounts of torsional strain due to that eclipsing interaction. And this guy will actually take on what is called a puckered conformation. We're going to talk about, so if this was perfectly flat and 2-dimensional, you wouldn't see this, but when it puckers, these guys can bend up. They do kind of move slightly out of that torsional arrangement. So it does slightly pucker, which helps alleviate some of that torsional strain. Okay, so then if that's cyclobutane, who's next? Pentane, right? So now we'll add in one more carbon, and we'll add in another carbon. So now we have 5 carbons. We try to make a bond here. It's much easier, okay? So now we're getting to that idealized 109.5. There's not a significant amount of angle strain, but now there is still some torsional strain, okay? So if we look at this nice little picture of our cyclopentane, and notice again that we're going to see these bonds slightly pucker. What we get is eclipsing interactions between this carbon and this carbon, right? So these guys, if I draw around, are all staggered. This is a staggered, this is a staggered, and this is a staggered, which is good. That alleviates torsional strain, but we still get an eclipsing interaction here. Eclipsing interaction, which is still going to lead to that non-ideal torsional strain. Okay, and we can't get rid of that eclipsing interaction in cyclopentane. So again, the angle strain is now significantly decreased comparatively to butane and propane, and we still have a slight amount of torsional strain from the eclipsing interaction. Okay, so now that's cyclopentane. So in theory, that should have been the best one. It wasn't. Instead, the most stable molecule ends up being cyclohexane. Okay, so cyclohexane is our perfect, idealized, most stable of our cyclic ring structures. Now, there's again a couple of reasons for this. So cyclohexane has no ring strain. There's 0 ring strain in the most stable conformation. This is because all of these bond angles are a perfect 109.5, so there's no angle strain whatsoever. Most importantly, in the conformation where it is the most stable, which is what we call the chair conformation, there are 0 eclipsing interactions. So if you draw this in the chair, you can go around and look at all the bonds and find everyone is in the staggered conformation, okay? So now, why a chair? I know it's hard to see this, but notice, what does this look like? If we follow just the backbone of carbon, it looks like a lounge chair, right? And so that's why they call it a chair conformation, okay? This is the most stable conformation of cyclohexane, okay? Again, why is it stable? Well, there is no angle strain and there is absolutely no torsional strain. All of the carbons are in the staggered conformation. It's also really important at this point in time to be able to visualize the Newman projection of cyclohexane, right? So let's imagine that we are looking down this bond axis here, and let's say that we're going to call this carbon 1, 2, 3, 4, 5, 6. If we draw the Newman projection looking down these bond axes, our front carbon over here is right here, right? Our front carbon over here is right here, and our back carbon for this guy is 6, whereas this guy is carbon 4. This thing in the middle is carbon 5, and this thing up front is carbon 2. So this was 1, 2, 3, 4, 5, 6. And again, all of those are in the staggered conformation. Okay, so that's the most stable conformation for cyclohexane, but there is another conformation that it can interconvert to that we focus on as well, right? So again, all of these bonds can rotate, right? That's the entire purpose of this. So if we take this from the chair and we flip this bond up, it enters what is called the boat conformation, right? So why is it boat? Well, to me, it kind of looks like a boat, right? So this is our boat. Now, this is not as stable. The chair is more stable. This is the higher energy conformation. So this is higher energy. Now, why is it higher energy? We still have no ring strength. So these are still perfect 109.5 degree bond angles. But now, if we look at our conformations, most of these carbons, so these guys, let's say these guys, and these guys, and these guys, and these guys are all staggered, which again is energetically good, energetically stable. It's these two carbons here and these two carbons here that have moved into an eclipsing conformation. So these guys are eclipsing one another, which is introducing torsional strain. So this is why the boat is higher energy. Where did my boat go? Boat. This is why the boat is higher energy, because we do have these two sets of eclipsing conformations, which leads to torsional strain. Okay, so again, lowest energy is chair. All right, so chair, we can find it again, is here. Okay. At room temperature, though, depending on the groups that are on our little cyclohexane ring, we're going to be able to see conformational changes between our chair into what's called the half boat, into the boat, and then into the other half boat, into the other chair. So there are two energetically stable versions of this, one chair and the other, and they can rapidly flip back and forth between the two at room temperature. And they do, and that's going to be a big important point, okay? So notice when I'm doing this, I call this a ring flip, right? So I take my ring, we rotate into the chair, and then we rotate, the boat, and then we rotate into the opposite chair. This is what I refer to as a ring flip. This is not just flipping the ring. That doesn't work, right? When we're flipping the ring, we are taking one ring conformation, one chair conformation, converting it to the other chair by rotating bonds. Okay, so this, going through all of these various energetic conformations, is what is called a ring flip. Again, it's not just taking the ring and flipping it over, it's actually rotating these bonds, moving it through its higher energy conformations into its opposite chair. Yes?
And all that energy is hot temperature?
Yes. Yes, most of these, especially for a non-substituted cycloalkane, cyclohexane like this, would be able to do this at room temperature. Okay, so then one other thing that I didn't mention, there is another reason why the boat is energetically unfavorable, right? So if we go back up into the boat, notice that if we had groups here that are at the top of this boat, so if we had, let's say, a methyl group here, and then another methyl group up here, and we're in this boat conformation, what's happening between these groups? They're repulsing each other, right? So we've got a lot of steric interaction here, steric interaction here. This is what we call flagpole interactions, and it's another reason why the boat is energetically unfavorable, it's energetically unstable, because of this steric interaction in the flagpole position. So one other reason is our flagpole interaction in the boat. And again, that's just going to be due to steric interaction. Yes?
What is a twist boat?
A twist boat is kind of like, so it moves from, pop these off. So we're happy, we're super stable, and one chair, as we move in to the boat, right, we go through a really high intermediate half chair, and then whenever it's here, it finds a nice little kind of stable thing in the twist boat before it moves into the fully boat position.
Okay.
So these are all of just different transition states along this progression from chair to opposite chair. So it goes through a lot of different states in going from one chair to the other. Okay, so we're going to spend a lot of time with cyclohexane because, again, it is the most stable of our cyclic alkanes. But before we can really do that, we need to be able to draw the correct structure of these chairs, right? So what we've been drawing thus far are just a nice two-dimensional hexagonal structure. We're now going to learn how to actually draw these chair conformations. So I'm going to go through this. There's some key little bits and pieces I want to mention, and then I'm going to let you guys draw a couple of these on your own. So I always preferentially draw what I'm going to call the right-handed chair, and I think most people draw the right-handed chair first. But again, there are two versions of this, and we're going to go over how to draw both of them. So if we are going to draw what I call the right-handed chair, the first thing that we're going to do is we're going to draw a shallow V. Okay, so what does shallow V mean? So a shallow V is not this. That is not a shallow V. That is a very narrow V. Okay, so we don't like that. That's not what we're going to start with. Instead, we're going to draw a very shallow V-ish. Big fat V. Wide. Very hungry V. That's step number one. That's our shallow V. Okay, so now step number two, what we're going to do is we're going to draw a little dot, dot, dot line down the middle of our V. And we're going to go from the right-hand side, that's why I call this the right chair. And we're going to draw a line that's about 60 degrees from that down, that's going to end right before that dotted line. So we have our shallow V. We draw our nice line at 60 degrees down and stops right before the little dotted line that we've drawn. Next, we're going to draw another dotted line. We're going to go over to the end, to the left-hand side of our V, and we're going to draw a dot, 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 directly down. We are then going to start here where we ended, and we're going to draw a line that's parallel to this guy, and it's going to end right before that dot, dot, dot line. That may be a little too much. We're going to go with it. I hate drawing chairs anyways, so. Okay, so now, once we're here, we're going to draw another dot, 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 but it's going to be down here, dot, 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 that kind of ends where this guy has gone down to. And what we're going to do is we're going to start at this left-hand side, this guy, and we're going to draw a line down that's parallel with this guy over here. So this is going to go down, and it's going to end where that dot, dot, dot ends. Then finally, we're going to connect the dots, right? So we have this guy, it needs to be connected with this guy. We're going to do that with a line that is parallel to this guy. So we connect that, we have ended up with our chair shape. So what we end up with here are three sets of parallel lines. We've got our red parallel lines, parallel to one another, our black parallel lines, and our blue parallel lines. And again, this is what I refer to as the right chair because this position is pointing up. The rightmost carbon is the position pointing up when I draw this. Okay, so I'm going to do it one more time, and then I'll let you guys do some on your own. Okay, so first step. What is the first step? Shallow V, right? So we get a nice shallow V. That's where we're going to start. Second step, we're going to start on the right-hand side, draw a line down that's going to end before that dot, dot, dot. We've got another dot, dot, dot. Over on the left, we're going to draw a line going up parallel to this guy. So I'm going to move it into red. We're going to be parallel here. And it's going to end before the dot, dot, dot. We're then going to dot, dot, dot below. We're going to draw a line starting on the left-hand carbon up top, going down to the dot, dot, dot. That's parallel to this guy. And then finally, we're going to connect the dots. And again, that final line is going to be parallel to this line over here. That was part of our shallow V. Okay, so with that, I want to get you guys practice. So you will be turning these in, so I would keep hold of them, maybe write them on a separate sheet of paper. But I want you to practice drawing 3 of those cyclohexane chairs. Okay, so go ahead and get practice doing this.
Part of the quiz this week, you guys will actually be drawing these, and you'll be uploading either a photo or a video of them for grading. So make sure to get a lot of practice and that you're satisfied with your ability to draw these cyclohexane chairs. The other thing I would note is later on we'll be adding in different things off of these chairs. So you may be comfortable doing that. Make sure that you're comfortable doing the other things as well. And then that's actually what I'll be asking for in the quiz. Okay, so make sure you're comfortable making these and that they're pretty and nice and that I can read them.